Okay, so take two, because I was not recording my voice. Okay, so we're going to start with hemodynamics. This is class one and two, probably. By the time you come to this class, you've already done turning your hemodynamic concepts, which is due before you come in. Some of the basic concepts of hemodynamics are cardiac output, cardiac index, mean arterial pressure, systemic vascular resistance, pulmonary vascular resistance, stroke volume, and obviously heart rate. So I need you to know all these concepts so we can start understanding hemodynamics. Let me go ahead and open, I'm going to share my PowerPoint so we can start talking about these concepts. I had it open and then, things happen. Okay. Here it is. And I also have some videos for you on these modules so you can get familiar. So what do we do in hemodynamics? Hemodynamics is what we call right heart study. In right heart study, we are going to take a look at the pressures inside of the heart. This is we get the information, the studies, and see how the patient is doing hemodynamically, what is happening inside of the heart and the lungs, the cardiopulmonary system. Okay, so the first thing that when we go to the cath lab, the first thing we do is an angiography, right? We take a picture of the coronaries, maybe an LV, but then it does not give us the whole information about the heart. And when we do a left heart, we get information about the coronaries, but we don't get any information about the pressures, the valves, the regurgitation, or anything that is happening inside. We can only see the muscle being irrigated by the coronaries on the left heart. So this is when hemodynamics comes on board. However, it comes with a little math. Who likes math? I like math, so hopefully it's not too bad. And I know some of you are already familiar with these concepts, but let's go and work on this again. So I'm going to grab some of my tools right here to kind of explain. So I have a little circle here. For example, this is aortic pressure, and we have three elements in when we read it like this, right? We have systole, we have diastole, and then we have mean. That's what the third one means. If we look at the left ventricle, we have systole, diastole, and mean. And we're going to learn how to do the mean. But this is just a sample so you can learn how to read these things when you read, information from a patient. Now, what kind of information do I need from a patient when it comes to my cath lab and do a right heart study? Well, the first thing that I need is height and weight. Now, as you can see here, it says 68 inches and 177 pounds. However, in medicine, we always use the metric system. As you can see, it's been already converted. Now, why do I need height and weight? Because I need to get BSA and I need height and weight to obtain this information. Let's work real quick how to do the conversions, height and weight, because sometimes, hopefully the systems are always working, but I don't know, it might not be the case. And it's probably a good practice for you just to learn how to do it manually. Okay, now in our systems, all you have to do is enter your patient information in height and weight in inches and pounds. Okay, let me see if I can. I'm a little sick, so I hope you don't mind a little coughing here and there. Okay, so in this case, for example, this patient is 5 feet and 8 inches, right? So this is this patient that I'm looking at on the screen, and the weight is 177 pounds. Okay, so the first thing that I'm going to do, I'm going to work on the height, which is 5'8". The first thing that I have to do is convert into inches. So what I'm going to do is I'm going to convert how many inches are in a foot. If you answered none or 12, hopefully it's 12, this will be equal 60. Look at my numbers, 60. And then, as you remember, I do have 8 because my patient is 5'8". So I'm going to add 8 inches. So this patient is going to be 68 inches tall. Typically, when you ask your patient what's your height, they're not going to tell you, oh, 68 inches. They're going to tell you 5'8", 5'3", 6'1", whatever it is. So you can get that. Now, once you have gotten the inches, you are going to get 68, and then you are going to multiply by, this is a constant, 2.54. Now, I'm going to give you a calculator so you can calculate that. I'm going to pull my phone and do this real quick. So it's 68 times 2.54, and it is 172.72 centimeters. That's my result. And make sure during all this class that you actually add the units. It's going to be super important. If you're missing the units, you're going to get half of the points. If you don't have units in there, you're going to miss the points. So make sure you do add that information. All right. So that's my height. Now let's take a look at my weight, 177 pounds. So what I'm going to do here to convert, the only thing I have to do, 177 divided into 2.2. That's what I have to do. This is a constant for weight. So now this is 177 divided by 2.2. It is 80 kilos, 80.5 kilos, kilograms. So make sure when you add this information to your patient that you add or to your exams in this class, make sure you add centimeters and kilograms because we need to work with the metric system. Just have to remember that 2.5 and 2.2 are constants. So for weight, for height is going to be 2.54, and for weight 2.2. That's a constant, right? It's a rule in math. Let's put it that way. Okay. Okay, so what you can do now is you can get your height and practice with your height and see what is your number. We might have done it in class. If not, you can go ahead and try for that. And you can obtain that. Now let's take a BSA. So BSA is body surface area, right here. Why is it important, body surface area? Because if I get to extend the body in a 2-plane, that is 1.92 square meters. So that means if I extend all my tissues and put them on a flat, is going to be, in this case, 1.94 square meters. This is so important because we're going to base medication on BSA. The doctors might ask you, and this is good as a tech, that you are always paying attention to your patient's height and weight, because the doctor is going to ask, how much does the patient weigh? And then if you're fast to answer, hey, 80 kilos. You're not going to say 177 pounds. You're going to say 80 kilos. And they're going to be like, oh, they know. So this is great information, especially coming into the lab. Okay. Now, on this sheet of information, we also have some other things like saturations we have here. We haven't talked about that, but we will. Bells, we're going to talk about that. We're going to learn how to do that. And I think that's it on this page. So I'm going to go ahead and erase everything so we can move forward. So make sure you practice those conversions. You need to know those by hand. All right. Now, we said the first concept that we talked about coming into this class, it was cardiac output. Okay, so the concept of cardiac output is the amount of blood pumped by the heart per minute. So it will be liters per minute. And we're going to talk about the units here in a little bit. So in this section, we're going to talk about cardiac output, and different ways to get cardiac output, fake thermodilution, and angiographic. We're also going to talk about regurgitant fraction, vascular resistance, and valve areas. So let's talk about cardiac output. Like I said before, cardiac output is measured in liters per minute because we want to know how many liters is the heart able to push. Now, normal, remember, patients that we have in the cath lab probably are not normal. When you see this number, it's going to be like, whoa. So a normal or healthy person, average size, is going to be 5 liters per minute. 5 liters per minute. Okay. Now, when every time you see index, the word index after it, for example, we have cardiac output, say we have 5 liters per minute. And if we divide by BSA, that's going to become cardiac index. So we are going to have liters per minute per square foot, per square meter, because we're adding the BSA, right? Okay, so I'm going to leave the QS and the QP. I'm not going to talk about that right now, but based on this image, just to give you an idea, we have systemic. We have two information here, systemic and pulmonic. The systemic blood is what goes outside of the heart, the whole system, and the pulmonic is what goes to the lungs and comes back. Okay, but let's just not get into that just right now. And if the patient is healthy, it should be also 5 liters per minute, right? The problem is when it's not. And then the ratio between these two, it should be 1 to 1 because this is a normal, healthy patient. But when our patients come to the cath lab to do a right heart study, chances are the numbers are not going to look as good. Okay, so let me just remove this clear and we continue. All right, let's talk about cardiac output. How do we calculate cardiac output? Now, there's different ways to calculate cardiac output. Now, this particular formula is an assumption, it's an assumed cardiac output. I will never recommend that you use this cardiac output formula for an exam, for example. This is just kind of like when you're just walking by and then you just need to know really quickly, okay? We are going to use, for this particular formula, we are going to use information as cardiac heart rate, and stroke volume. Okay, and this is where we're going to start applying the math to get cardiac output in a non-specific way. When we're doing a study, we don't want to use this one. So when we get to our test, we're not going to use this formula. This is just like a run by calculation, just to determine really quickly. Okay, so it says here, assuming that my patient has a heart rate of 80 and a stroke volume of 85 cc's or milliliters, all I'm going to do is I'm going to multiply 80 by 85. And my result is going to be 68 cc's per minute, which is 6.8 liters per minute, right? Remember, cc's are equal as milliliters. So this patient will be doing 6.8 liters. And if you know 5 is normal, that means this patient is a super patient, right? It says here normal cardiac output is between 4 and 8 liters. It depends on the patient's size. And if it's female or male, typically males have more more blood in general in their system than women. But anywhere from 4 to 8, I've never seen anybody 8. I have seen 6.2 as the max. And I've seen very low as well. 2.7 or things like that. I mean, they're really bad. Okay, so this is basic. And remember, this is not what we're going to use for your exams. Okay, by the way, you're going to have to demonstrate your work when you're doing these equations for this class. So this is just like a walk by. Okay, now, remember we talked about cardiac index related to BSA, like the body surface area. Now, these two individuals right here, their heart pumps 3 liters of blood per minute. Who do you think feels better? The larger person or the smaller person? Well, the smaller person, because it's less body surface area. right? There's enough nutrients, enough oxygen, enough hemoglobin to get around the body. That's about good. That's about the size for a kid, right? 3 liters per minute, because we talked about 5 liters per minute being like a normal standard. So this person, I don't know how tall or how big he is, but I know he should be somewhere around 5 or 6, right? So if he's having a 3 liters per minute, that's a problem for him, right? He's not having enough irrigation to his body. Okay, how do we get, excuse me, how do we get cardiac index? Like I said before, every time you see index, all you have to do every time you see index, you're going to have to divide by BSA. We already have, in the case of before, right, we already have established cardiac output and I have a BSA because I already have my patient's height and weight, then I'm going to be able to do a cardiac index. Now, a normal cardiac index between 2.5 and 4 liters per minute per square meter. Remember, when we add index to anything, and you're going to see how we have index in several formulas, whatever the units are for the specific formula, for example, here, cardiac output liters per minute, and then divided by square meters. So make sure you work on those units. Okay. So we have a formula here of BSA that we can get here in class. We're going to use a chart online so we can get that because it's a very complicated formula to get to the BSA. So let's not worry too much about that. We just need to know the types of BSA formulas that we have. Okay, let's go on to the next one. Okay, let's talk about cardiac output. Cardiac output, like I said before, it measures the amount of blood that is ejected from the heart each minute. And there are 3 ways that we can resolve for this cardiac output information. One is angiographic. That means we can take an angiogram. Remember when you take your LV, for example, we can see, we can determine. So we're going to talk about that. Angiographic is by X-ray. Fic, which is a formula, and thermodilution, it's another formula with an addition of fluid. All 3 can be determined in the cath lab. But just remember, you have to know this concept. Cardiac output is the amount of blood ejected by the heart each minute. Okay, so we're gonna head on to the first formula. It's going to be angiographic stroke volume. I'd like to say we're getting to the first part of the equation. If you remember before, it was stroke volume by heart rate, right? So we need to determine stroke volume. I like to think on these formulas, like I said before, about related to the kitchen, and I will always talk about the chicken parm. If you want to make chicken parm, you need the ingredients for chicken parm. So you open your pantry and you can have so many ingredients, but you don't need all of the ingredients in your pantry to do or to make chicken parm, right? You're gonna need crumbs, tomato sauce, chicken, and very specific items, right? But for example, I don't have the breading, but I do have crackers. So I have to transform the crackers so I can make the crust. Yeah, so I want you to think on that concept. Sometimes you have to look further and see if you have ingredients to make one ingredient to plug into the formula. Okay, all right, so the first formula that we are going to see is stroke volume. Okay, so the stroke volume, let me just get an annotation here. This is my formula here. Stroke volume is the end of diastolic volume and the end of systolic volume. Now, how do I do this? I am going to take an image when the left ventricle is like expanded all the way in diastole. And then the second picture is going to be when my left ventricle is in systole. And then the only thing that I'm going to do is deduct one from the other. And that's how I'm going to get the stroke volume by angiographic method. This is just the stroke volume. okay? Now, the average stroke volume for adults is 70 milliliters. That means every beat, the heart pushes out about 70 milliliters. That left ventricle pushes out about 70 milliliters. Now start looking in your labs every time we do an LV. What are they looking for, right? What is the amount? If they do it by angiographically, what are they measuring, right? How can they see the two, and how do they measure? We have little calipers that you can see. Okay, this is important information. Stroke volume is your first formula, end of diastolic volume, and end of systolic volume, and the 70 milliliters as probably, we need to know what normal is, right? So 70 milliliters will be your average for a patient. All right, now remember that I said that get the bread to make the crumbs, right? So you needed to get stroke volume in order for you to use it in another formula to get cardiac output. And so we have the information here. This is our angiography taken in with a pigtail, right? And then we measure both. We have systolic, and you have it here. We have systolic and we have diastolic, right? So we can put in here the information. We have a left ventricle end of diastolic volume, which is 148. We have it here. Let me see if I can add my circle here. Okay, so we round it to 148. And then here, the end of systolic is going to be 84. So we're going to plug in the numbers, right? At the end of diastolic, and then minus the end of systolic. So the end result is going to be 64 cc's, 64 milliliters, which is pretty good because the normal is about 70. So this patient is kind of pretty good. Now, our patient's heart rate, we're going to use the first formula. The heart rate on our patient is 80. And if you remember the first formula that we use, the walk by, right? It's heart rate by stroke volume. Now we have the two pieces of information already, right? I have the heart rate, which is 80, and I have the 64 for stroke volume, right? 64. Now my cardiac output, now I want you to pay attention on the units, right? I have cc's. Remember, cardiac output is liters per minute. CC equals, let me just type it in here because you might need to remember this. CC equals milliliter. Okay. All right. Let me erase everything here. So in this cardiac output formula, I am going to multiply 80 by 64, and my result is 5,120 cc's. But that's not my unit for cardiac output. So I need to convert into liters per minute. So that means I have to move my decimal point 3 times to make it 1,000, right? Instead of milliliters, I'm going to have to move and make it liters per minute. So that's why I have 5.2. So I'm going to move 1, 2, and 3 points, and I'm going to get a point here, 5.12 liters per minute. Yeah. Okay. This is super important. If you give the result in cc's, it's not complete. You're going to get points taken off. It's just paying attention to all the details. Cardiac output is always measured in liters per minute. All right. And since we are here and we have some pieces of information that we can work to get some other information, we do have ejection fraction percentage. So to obtain the ejection fraction, we're going to use the stroke volume and the left ventricle end of diastolic volume. We're going to divide. So I already have stroke volume. Let me remove all this. And I'm going to grab my arrow here. So I have my stroke volume is 64. And I have my left ventricle end of diastolic at 148. This is to get the ejection fraction percentage. So this patient, the ejection fraction, and I have it here if you can see it here. So we did it manually here, and here the computer did it for this particular patient. So in all the cases, we're going to be able to see these numbers in the computer. But it's always good that you know how to get there. So the ejection fraction percentage is going to be 43%. Okay. Okay. Remember, that was by angiography, by picture. Yeah. So we need to get a pigtail, take an LV, shoot the contrast, and I can take systole and diastole here. Okay. Now we're going to take our next cardiac output formula, which is the FIC cardiac output, which is known as the gold standard to determine cardiac output. On your RCIS, you might have this question: which method is considered the gold standard to obtain cardiac output? Or it might be worded in a different way, but it is FIC. Now, in order for us to get the FIC cardiac output, we need more information than what we had before. So this formula is a little bit more complicated. We need the oxygen consumption and the oxygen that the patient is using, arterial and venous. So let's see what it looks like. So you have already been in lab, and Ms. Vasquez has already explained to you that as you go through the right heart, remember all this we're doing is a right heart to get thermodilution or FIC, okay? You need at least 2 samples as you're traveling in with your Swan-Ganz, right? At least 2 blood samples. They might need 1, they might need 2 or 3 or more, but at least the standard is 2. So we are going to analyze the blood. We're going to get the samples, and you've already probably seen it in the labs, right? We get the samples, send it, give it to the nurse or to another tech, and then they're going to run it, and then they're going to give us information, right? They're going to give us oxygen and hemoglobin back, right? So we need arterial and PA, if nothing else, right? But let's see, what else do we need here? Okay, the oxygen content per 100 milliliters of blood is about 20 milliliters. So 1/5 of the blood is oxygen. Okay. You were also going to start looking at the blood and what the color looks like. I mean, we know we don't have blue blood, right? But there is a difference between arterial and venous blood, which is going to look a little bit more like number 4 here, a little bit on the burgundy side, right? So if you see like bright red, it's arterial blood. And if you see this or this, is venous or less oxygenated. We're going to be able to see this like when the patients are like this oxygenation is like on the 70s, it's going to look like this. So you more or less are going to be able to determine as you go and as you learn, with your hemoglobin. Let's clear this and let's move on to the next one. I want to see if we can get to, okay. So we're going to start working here with some information to start getting to our FIC formula. The first thing that I need to obtain is the VO2. This is the formula to get the volume of oxygen. 125 is a, let me get what do I get? An arrow. Okay, that's a constant. 125. Always. 125 no matter what. If it's you, me, Ms. Vasquez, Mr. Ochoa, whoever it is, constant. Constant will always be the same. Now, what is not going to be the same is the BSA. Everybody's going to have their own BSA. Remember on the previous case, it was 1.9. Everybody's going to be the same. I mean, everybody's not going to be the same. So this is when it comes height and weight individually, and it's going to make a change here. So to get VO2, the only thing we're going to do is we're going to multiply BSA by 125. Now, normal BSA, and remember, if you want to make a list of what is normal on the numbers, like cardiac output, cardiac index, ejection fraction, stroke volume, things like that, if you know what is normal, then you're going to know when it's not normal. Okay, so a normal VO2, let's put it that way, is going to be 250 milliliters of oxygen per minute. Make sure we have the units. So in the case of the other patient, it was 1.9, so it's going to be a little bit less, but that makes sense because probably the patient is smaller. BSA rounds around 2 meters, 2.4, 1.9. Okay, so this is how we get VO2. We're still gonna gather in the ingredients, right? To make that chicken parm. Okay. All right, and then we get to the fake cardiac output formula. Take a deep breath. This is not hard. We just have to pay attention on the details. Okay. Okay. So we are looking at the formula, and we are going to get all this information that we already know how to get. Okay. Let's see, for example, O2 consumption, right? The VO2, it will be 125 times BSA. And that's how I get the O2 consumption, right? And then I have here the arterial O2 and the venous O2 difference. I need to know the difference. So let's not look at the bottom right here where it says 20 and 15. Don't get cross with that. Let's just take a look at the top part. Arterial and venous. And it says the difference, so we have to reduce, right? And then outside, we have to multiply. This is super important because if we miss the step of multiplying, right? It says multiplying by 10. Yeah? Arterial, venous, difference. We need to, yeah, there is more steps to get the arterial and the venous and then the difference. So let's keep looking into that pantry. Okay. Let's remove here. Now, let's take a look at the difference, right? Now, let's understand AB difference will be this AB difference. Maybe I need to put it on a mark, right? This AV difference is this AB difference. Yeah, we're working on the difference. We need to know the difference between arterial and venous. Yeah, what is happening when the heart leaves when the blood leaves the heart to where the blood comes back to the heart. We need to find that information, okay? Or leaves the lung, come back from the lungs. So let me just take this. I need to remove. I don't know why I have to remove all my drawings before I can move on my next image. All right. All right. So I'm going to have to get the AB different here. AB difference, arterial, venous difference. This is just some information I'm going to get here. This is my first formula. Okay. Okay. So let's take a look at our first. This is the formula for FIC. Assume VO, and then we have the arterial venous difference and multiply by 10, just like we have been seeing. I'm gonna get a circle. Okay, so I have my patient information here on the side, right? I have predicted O2. Okay, I'll take it. And then I have hemoglobin, super important, hemoglobin. I have my BSA. And then I have my arterial blood saturation and I have my venous saturation because PA is deoxygenated blood, right? Even though it's a PA is pulmonary artery, we know it's deoxygenated blood. So I have all of the elements to get my chicken parm. Okay, so let's go ahead and plug it into our formula. All right, so it says here predicted O2, and sometimes you're going to see that we do a test. It's a metabolic test in which we can get the true O2, where we can get it straight from a machine from a patient, or we can use some predicted information like this. Okay, so in this case, we have assumed VO. Remember, it says 125, just like it says here, right? And we said that we're going to multiply by BSA. Remember that? The VO is the constant 125 times BSA. In this particular case, my assumed BO is going to be 250 milliliters of oxygen per minute. Make sure you work on the units. All right, now let's take a look at my next part of my equations. I need to work on the difference, right? So I'm going to work on my arterial O2 saturation first. 1.36, it's another constant. I know there's going to be a lot of constants. It becomes easy. Okay, the next part of the formula, 13, is my hemoglobin. If my patient's hemoglobin was 7.9, here it will be 7.9. Yeah? All right. And then if I'm working on the arterial side, the oxygenated blood, I'm going to put, it says here in the information, 98%. So I'm going to do 0.98. Yeah, so all I have to do is do the multiplication, and it's going to be 17.3. And then I'm going to do the same thing on the venous, constant 136 by hemoglobin. And then I'm going to go back and read my PA, which is 61%, 0.61. And my result is 10.8. Okay, now I'm going to go ahead and now, just now, I'm going to be able to plug all these numbers into my equation. Okay, because if you remember, my equation is right here on the top. Let me just get an arrow. This is my formula, right? So I'm going to do my assumed VO is this 250. And then I have my arterial here. And then I have my venous here. And then I have times 10. Correct? So I'm going to resolve for all this. So I like, instead of resolving everything at once, I like it for me, for my own sake, to do one thing at a time, right? So I like it how it's here, in which I can resolve. I already have the first part. I don't have to do anything for the top part, right? So I'm going to leave it like that. But then I like to resolve the bottom first. So I'm going to do this equation first, 17.3 minus 10.8, which is my arterial and my venous, and then times 10. So I'm going to resolve for that, and then I'm going to plug it in. And then once I have these two numbers, I can go ahead and do my division, and my result is 3.85 liters per minute. So it was just a matter of looking where the items are. When it says here volumes percent, that unit does not need to be added to the formula. So just remember that your FIC or the cardiac output in general has to be at the end liters per minute cardiac output. All right, so let me see what is next. I think there is another sample. If not, okay. All right, so I'm going to leave it to this because that's a lot. So we're going to start practicing. I'm going to give you some information, some patient information, so we can start practicing and getting this information. So we can start getting used to it. So that's it for cardiac output. We still have thermodilution, but I'm going to explain that on the next class. Okay, FIC by thermodilution, which I'm pretty sure you've already also seen in the lab with Ms. Vasquez, or you've already probably seen it in the lab where we get, take the different samples, etc. But I'm going to leave that for next because I need you to be like super familiar with this because chances are you're going to need this formula on your RCIS. Okay. All right. Well,